Hello, friends. Thank you again for joining our coffee session. And we had a great session. And I really thank you, everyone who joined in this festive season of Christmas and New Year. And they have sacrificed, their few hours of their holiday season enjoyment time to join us. Thank you again. So I just wanted to give highlights on some of the key discussions that we did during this session. And one of them is reachability analysis. And the reason, why organizations are facing the key challenge of, prioritizing vulnerability fixing is that there are too many vulnerabilities to fix, and there are various reasons because of which organizations cannot fix all vulnerabilities, and possibly I think some of them we discussed are like there are too many libraries to upgrade. Yeah, because this may be because organizations have access to a lot of tools now, and they are using the tools to identify all these critical high, medium, low vulnerabilities, and then they know that which libraries they are vulnerable and so on, but they cannot simply just fix them because upgrading them may break the code, may require testing, a lot of engineering bandwidth and so on. Yeah, so there are various reasons why libraries cannot be upgraded. uh, and sometimes, in a release, developers, when there is a vulnerability, developers do not have enough time to even test whether the library upgrade will work or will not work. So they need a tool, that can really prioritize them apart from just CVSS score. As you know, that CVSS score is primarily just because if everything works well, the vulnerability is exploitable, not exploitable, and if it is exploitable, what is the real impact and so on. But then it also has an element of prioritization, which is temporal score and environmental score, which is actually is not being considered because it does not have the context of the organization. And as a result, many of the high severities probably may not be high severity vulnerabilities, right? And as a result, one of the important technique is whether, you know, how to even prioritize these vulnerabilities, right? Now, some ideas that we discussed, such as, if it is direct or transitive dependencies, then probably direct dependencies, vulnerabilities in direct dependencies should be prioritized first. I think that's a very good idea. Second idea being business value of the application. Prioritize vulnerabilities and libraries to upgrade based on the business value of the application. I think that's another interesting idea. One of the idea that came is whether if it is external versus internal application, then external should be prioritized first, and internal should be prioritized, can be prioritized later if it is a conflict of time, right? And so on. I think there were other couple of good ideas, and the key important thing is that the ideal case, the vulnerability should be prioritized based on the risk, which is probability and impact, and probability should be determined by exploitability path, which in a way is a reachability path, but there is a subtle difference. And also the impact, which is the what is the impact when the exploit is successful, right? So based on these two, based on some of these ideas, I think the vulnerabilities can be prioritized. Now, before even we go to a demo of how we can use the COFE, our new tool, to find out which vulnerabilities to fix first and so on. I also want to highlight that there are a couple of tools available to identify vulnerabilities, such as dependency, GitHub dependency graph. Is one of the feature of GitHub where it has started, getting the dependencies from the source code and showing it in one single place. Second, OS dependency check. There's another tool maintained by OS, and SafeTap has its own tool, which is open source, called VET, and And an interesting thing is that all of these tools actually do a great job in identifying vulnerabilities, because it is not easy to, uh, the, the task of identifying dependencies is not straightforward in many cases, such as a project, say a project can have many manifest files, such as in case of Python, it can be requirement.txt or setup.py or my project.toml and various others. And then this requirement.txt itself can have various versions. Even in setup.py, if you it's a Python code, they can be requirements can be specified in many cryptic forms. It can even be dynamically computed, actually, based on various logic, based on the underlying operating system, based on the build environment, and so on. As a result, the exact and also the requirements may not be pinned to the exact version. They can have multiple various versions, available, and so on. So as a result, identifying dependencies and their direct versions is not possible in many ways to find out, right? So it has to be a maybe an approximate match somewhere. On top of it, in Python, in the case of Python, like we took an example of one of our demo project, which is the case for many of the projects, that in requirement.txt, many of the dependencies are pinned in a flat way. So there is no way to find out if there is a if the dependencies, like which one is a direct or indirect dependency. Yeah. So our vet, just take an example from a vet. What it does, it actually scans the code. Okay, it finds out the manifest, and then it go and we have our own database of vulnerabilities, similar to GitHub advisory. We source it from different places, and we also do a match to identify these vulnerabilities. So just a quick demo of vet, because vet is the prerequisite for our next tool that we will discuss. In order to run the next tool, we need vet to be installed on the local system. So in order to install VET, you need to go to our go to GitHub and search safe dev vet, and then it will have some instructions how to install it. One of the straightforward way, if you're using Brew, is to use tab, Brew tab. Second straightforward way is to just directly install as a Go package. Go, just by running this command, go install vet main, and then you need to configure its key, because it needs some access to the backend. Interestingly, we have a community version, addition of the key available. You can go and install it, and you can also run a command, to verify if the key is valid. So I'll just quickly check if that is installed on my system. Yes, it is installed and it is in community mode and the key is valid. Great. So once the installation is done, the straightforward way to run vet is just run vet, sorry, vet scan -d, and just scan it. Yeah. So what it's going to do is going to identify the manifest. It has identified, like, there is one manifest requirement.txt, and in that manifest there are multiple vulnerabilities, multiple libraries, and some of them has some critical, high, medium, low vulnerabilities. And not only that finds vulnerabilities, but it also finds libraries which are potentially unpopular and may become a nightmare at some point. Yeah? Because unpopular libraries are not maintained, they may have vulnerabilities, they may be malicious, may get, malicious at some point. Uh, and then it also tell you how many of them are out of version, right? And then it has other interesting features, advanced features that you can customize, such as you can specify what of the exact files you can scan for direct dependencies. As I was telling before, there is no standard way. There can be multiple manifest file in a project, some for test, some for dev, and some for production, and so on. Now, one of the interesting thing is that you can also add, integrate wet along with your GitHub action, and you can check out the code, and the page you will find out. Yeah. So once the wet is installed, now the next challenge we have is how to prioritize these vulnerabilities based on traceability and path. So we took a interesting approach of finding out whether there is a path from the source to the vulnerable dependency, and we do it in multiple phases, such as first step is definitely reading. Say we have this app called pydemo2, and it has one manifest, say requirement.txt. So we first read it, we find out what, as per the manifest, these are my specified dependencies, right? That is a step number one. But then the challenge with this, just using this file, is that many of these dependencies are I may be transitive, and some of these dependencies are not even used at all actually, because sometimes what Python has no way, no restriction, or possibly no way to remove these dependencies automatically, as it happens, say in Go. Go is pretty good in that way. It remove unused dependencies automatically. Second challenge is that there is no way to find out which one is transitive dependency and which one is not. So what we do is we go to the code. We use well-known parsers like TreeSitter and other known parsers, and we go and parse the source code. And in the source code, we go and find out whether what are the dependencies which are actually imported, such as if I go to one of the files, such as say settings.py, it is importing two dependencies like this Django Heroku and OS. So we go and find out these dependency imports, and we also find out if they are being used at some point, such as this Django Heroku is actually not just imported but also used. One of its function is being used, right? Many times it may happen that the dependency is being imported but it's not used anywhere. That's possible. So we also take care of that to some extent. And what we do is that based on this analysis, we find out what are the exact direct dependencies used in this application and what are the dependencies which are not used in this application. And based on this, then we do this, this scan, this analysis recursively for all of its other dependencies. We download the code, we analyze the source code, we find out what are its exact dependencies and so on. Once we create this whole graph, we analyze this graph and then we reduce it to the exact graph which tells us the exact, find the exact direct versus transitive dependencies. Yeah. So I'll just quickly give a demo. Yeah, right. Say now this coffee, we can install it from easily. Go to the web page, our coffee web page, and say install it from there. Similar to similar to our wet. So we can install coffee, something similar. Go install GitHub coffee main. I think yeah. And the prerequisite it has is that it should have wet installed on your local system because it internally uses wet. Now, what next thing we will do is once it is installed, we can actually run the coffee on. We can find out what are the commands. Okay, so it has a command called scan, and you can specify a directory, which is this directory. And then it has a interesting feature that if you want to, dump this graph in a CSV format for further analysis, that also you can do. Then minus LL means no debugging. So if you want debugging statement, minus debug minus L, and this will print everything on on the console, but in this case, I don't want debug statements. I'll just say yes, go ahead. And what it is doing internally is running vet to find out, vulnerable dependencies. It has found like 33 potential libraries which are vulnerable, direct, maybe vulnerable and insecure libraries, potentially unpopular libraries. And then what it is doing, it is crawling recursively all the other direct versus transitive packages to find out whether they are really direct or transitive and to find out the reachability path. Okay, so this is what it is doing. Now we by default, it has a depth limit. Like there is a limit, we have set it to only level 2, but then it can be increased. If it is increased, it goes even further, and find out if there is anything. So you can see that after crawling, what it does, it analyzes the graph quickly and stem down the graph and then prioritize the vulnerabilities. And then it shows the vulnerability score as per COFE score and as per CVS score versus CVS score. And it also shows like how many vulnerability count found in that library, and the top vulnerability has a score of 10, and what it should be its actual score based on the reachability. So this library is directly used here, this library again directly used, but then this library is kind of a transitive library similar for this, and there are other libraries which are like more transitive in terms of path, so its score is reduced accordingly. So we are using a formula basically we reduce the score based on the length of the path for now. But this formula probably will improve as we go in the future, direction, right? So the coffee basically gives you a score that you can use to prioritize vulnerabilities not just by CVSS score but by transitive score. Now I was talking about the graph. So what you can do is you can copy this. So there's some CSV files it has created. So for a demo, what happens is that you know, uh, it dumps the graph. It dumps two kind of graph. One is the short, optimized graph after removing, all the unnecessary nodes, unnecessary packages which are not used, and one is the original graph so that you can see, what is the original ones. And what you can do, you can use a app called, you know, Cosmos Graph Run.app is just a library, it's just a library to visualize graphs. It you here you can actually uh, specify the input graph. So here what we are going to give. So Coffee actually produces four kind of files, four files. One is this is for optimized graphs. So this file is actually a set of ages, node from this node to this node, what age it is, and its relevant color and other information. And this file is the metadata of the nodes of the optimized graph. And same for original graph. This file contains the ages, and this file contains the metadata of the respective nodes. Okay. Now we'll show you what metadata contains. So let's import it. So we imported original graph from here. Click, and then launch. So this is the original graph for this. This is basically a small size application which has around 232 dependencies up to level 2. Yeah, and then we have other various various attributes of nodes and ages that you can use to highlight and color it. One of the attribute is vulnerability score, and second attribute is hygiene score of the app, like hygiene in terms of whether the package is popular, is securely maintained, and so on. And it's based on the scorecard score, right? So we will just focus on vulnerability for now. So I'll just say node size based on vulnerability score. So based on the vulnerability, the node size is increased. I will slightly reduce the node scale. Second, I'll also color it based on the vulnerability color. So you can see that now the vulnerability, red ones are the ones which have the highest critical vulnerability, right? And this node is our application, okay? And these red ones are the vulnerable nodes. And if you notice that many of the libraries are actually direct, many of the vulnerable libraries are direct dependencies because it is a flat file as we discussed, right? Now, as a result, it is just saying upgrade everything. So this is the first column we are talking about. This is a graph of this column, based on CVS score. Now we will, simply import the graph, which is optimized graph generated by COFE, and that we will do in a separate file. So again, I will load my demo CSV and then the metadata. And I'll say launch. And first thing you can notice the graph is reduced, okay, because unnecessary nodes are removed. Second thing, we will just color it up the same way, like I will increase the size of the node which are vulnerable. I will also highlight them with the color. Then I'll do another interesting thing is I'll also change the weight of the edges, like the edge width. Okay, now I'll just explain you what does it mean. Yeah. So actually what it means is that we also compute, we also assign a weight for each edge if it is coming from a vulnerable node. For example, this node, I'll just quickly remove the labels. So like this node, you can see that this node is 1, 2, 3, 4. So this is our main application. And this library is vulnerable, but this library is a transitive dependency, right? You can see there's a transitive dependency. As a result, the color of this edge is like little less. So this color is depend basically it's a priority of upgrading this node. Yeah. On the other hand, if you look at this node, because these are direct dependencies and their criticality, these nodes have color of these edges is little larger, little red in color. Yeah. So this is much better. Yeah. So you can see that they are the tool has identified, the transitive versus actually direct dependencies and also prioritize the dependencies upgrades. Like this color of these edges actually is the priority of these columns. So these four level dependencies probably is SQL sparse looks like, right? 1, 2, 3, 4, and its color is yellow, which means 4. I mean, not yellow here, but it's kind of 4, 4 or 5. Yeah. So anyway, the graph is actually just for fancy way of looking at it, but I think that this information is also good enough to consume, well consumed. And in this way, the coffee tool can help you to reduce the number of dependencies to upgrade. Its uses first of all, it optimizes the graph based on code scanning, and then it also finds out the transitive versus direct dependencies, and it also shows a path of potential exploitable path in case it is exploitable. Okay. That's it. I think this is interesting tool, and we will release it, in open source to the open source community very shortly. And we believe that we need your help and support. Please feel free to contribute. Uh, as a next step, we want to add support for Java. Currently, it supports only Python. So as a next step, we will like to support, other ecosystems too, such as Java and NPM. Uh, and feel free to, suggest and give feedback. Okay. Thanks. Thank you very much. Have a nice day. See you next time. Bye.